Assalamu alaikum ji. This is Muhammad Numan Aslam Khan and welcome to the lecture 11 of our course of numerical methods. Just a recap from the previous week. Till now we are able to complete our topic number 1, which is solution of a one variable equation, and this includes the methods bisection, fixed point, Newton's secant method of false position. And then we are also able to implement one of the methods, namely bisection method, on to the MATLAB. Okay. After learning some of the basic commands of the MATLAB, we have implemented the pseudocode of the bisection method that we derived in the lecture of the bisection method in the MATLAB. And we have seen some of the commands that can help us in actually implementing that code. Obviously, there will be many more ways, many more commands. I also discussed with you a straightforward command F0 that will give you a solution that you can use of the MATLAB. But the assignment you're just going to submit in a couple of days will help you understand more about the MATLAB, and it will be beneficial in terms of using MATLAB. Okay, so now we're moving to the topic number 2, which is the system of equations. Okay, so moving from a single variable equation to multivariable equations. Okay, and so we're moving to our topic number 2, which is a system of equations. And in system of equations, there are two actually systems. One is a linear system, other is a non-linear system. Okay, so in form of a linear system, you have a course of during your semester 2 of linear algebra. So we have discussed a lot about the linear system in that course. Hopefully you remember some of the methods, namely Gauss elimination or LU factorization. Okay, these are some of the methods that you learned over there. We'll be just doing them again too in this course, but obviously with a different perspective. Okay, and then there are non-linear system. Okay, so if you I've just written the examples of a linear system and a non-linear system. The example of the linear system is a special in a way that it has some symbols, namely w11, w12. Okay, so it is somehow probably you remember or not, it is actually connected with the application that we wanted to implement, as we discussed in lecture 1 of this course. We'll be looking into this example. Okay, so we'll be going to know what are these w1, w2, w4s at the end of obviously this topic. We'll be able to solve that problem. um, but the unknowns in this examples are x1, x2, and x3. These are the unknowns. So it's the linear system. We can convert into a form where we can use the matrices to solve it. The other example you just see is one of the example of the nonlinear system. So for example, if you see the second term in the first equation, which is cos of x2, x3, so it is a nonlinear term. So that's why that equation is a nonlinear equation, and it is sufficient. If in any system you got one term as a nonlinear term, then that equation will be nonlinear. Ultimately, that system will be nonlinear. Okay, so if you got a one term as a nonlinear in a problem, then then the total system is a nonlinear system. Okay, but we see many other nonlinear terms in this example, in equation number 2 and equation number 3, namely x1 square, x2 square, and then we have e power minus x1, x2. These are all nonlinear. So these are some these are an examples of how this linear system and a nonlinear system will look alike. Okay, so now we're moving to the linear systems. Okay, um, in both examples, the unknowns are x1, x2, and x3. We can have more than 3 equations. We can have 4 equations, 5 equations, or n equations. Okay, so moving to the linear system, we will be dealing in this particular lecture. So objective of this lecture is trying to understand what was the Gauss elimination, and we're just going to revisit that, and we will try to develop an algorithm of the Gauss elimination, and then we try to see what are the problems with the Gauss elimination and how can we solve it. Okay, so first of all, this is a linear system. Okay, so generally speaking, that's how the linear system will look like. Okay, so with n equations and unknowns, unknowns. So we have n unknowns, namely x1 to xn, and this is the coefficient matrix, and this is called the right hand side. And we normally treat this as ax equals to b. Okay, so you can just write it. So this is the equation that we are in. This is called the matrix equation. Okay, because we are dealing with the matrices. Now, there are a number of methods available. We'll be revisiting one, the famous one we already did, namely Gauss elimination and LU factorization. We'll be doing two more methods, but first we're just going to quickly revisit them, and then we'll see what are the problems with those in numerical perspective. How can we modify those the methods? Okay, so um, I am just starting this with the method of the Gauss elimination. Okay, hopefully you remember that when we start with the Gauss elimination, our objective is obviously to find these unknown vector x. Okay, and so what we started is we started to make an augmented matrix. Okay, what is an augmented matrix? A matrix which only contains the numbers. Okay, so which contains the coefficient matrix and the right hand side. The right hand side is b1, b2, so on to bn. Okay, this is the augmented matrix. And the objective of the Gauss elimination is to make this matrix, convert this into a form such that it is a upper diagonal matrix. Okay, so we wish to convert in an upper triangular form. Here, all the elements on or below the main diagonal are 0. Okay, they are 0. Okay, so that is the actually first step of the Gauss elimination, that it converts the augmented matrix into upper diagonal matrix. Once it converts into an upper diagonal matrix, then we use the backward substitution. Okay, so converting the system into an upper diagonal form, this is the step number 1, and step number 2 was the backward substitution. So what is the backward substitution? We have to, as we have written the equations into the augmented matrix form, we're going to write the augmented matrix form backward into the equations. Okay, but starting with the last equation first, which is ann xn is equals to bn. So this is the last equation. Okay, so from here you can find the value of xn, which is bn divided by ann. Okay, then you write the second order equation and you know the value of an, then you can find the value of an minus 1. Then you find the value of an minus 2. Ultimately, you find the value of, sorry. You find the value of xn, then you find the value of xn minus 1. Okay, from the second last equation, you'll find the value of xn minus 1, then xn minus 2, and ultimately x2 and x1. Okay, so that is the objective of our problem, that we wish to find the unknown vector x. Okay, so that's how we perform the Gauss elimination. So there are two steps mainly: converting to upper diagonal form and then doing the backward substitution. Okay, so The thing is, when we convert this system into the upper diagonal form, okay, we use the row operations. Okay, what are the row operations? Row operations are the operations that are allowed onto the equation. When you're solving equation, these are the operations which are allowed. Okay, for example, you can multiply with the scalars. Okay, you can add them, you can subtract them, you can change the position. Okay, so these are the allowed operations. Now I'm coming to actually the that particular form, that how to convert this into the upper diagonal form. Okay, so the step number one is, so step number one obviously in the changing a matrix, augmented matrix, into a upper diagonal form. Uh, this is called a pivot element. Okay, so the first element on the main diagonal, it is called a pivot element. Okay, so let me write step number one. Okay, um, choose pivot element A11. Okay, um, use it to make zeros below in all rows. Okay, step number one is okay. Let's say the pivot element is A11, and use this to make all this elements in the column one as zero. Okay, so we have to make them zero. Okay, uh, so once we done that, how the augmented matrix will look like? A11. So there are no changes to the row one. In the second row, this element has been changed, so obviously there will be some other changes. Okay, so there are changes. I'm just using the same notation just to, so there are zeros in the first column, but obviously there are different changes that are going to occur on to the other elements. Okay, so let's say after the first step, the matrix look like this. Okay, now we will travel the pivot element to the second position, which is on the main diagonal. We move on the main diagonal. So this is a pivot element at this position. Now we'll use this pivot element to make all the elements in this column below the pivot element as zero. It will make all entries as zero. Okay, and we continue this until the second last equation, which will be pivot element will be an minus 1, an minus 1, and in the last equation there is a and n, and obviously when a and n will be a pivot element, there is no element below it. Okay, so we have to stop the operation. Okay, with this, while moving on to the main element, will make all the elements below the pivot element as zero. Okay, so that matrix will be with us after the end of this particular practice. Now the thing is, uh, for example, at the first pivot element, what are the operations which are allowed? Obviously, we can, as I already told you, we can multiply by the scalar. Okay, we cannot multiply by the variable because that will change the linearity of the equation. Then equation will not be linear. Okay, so We can multiply by the scalars, and we can swap the rows. It's not a problem. We can change the rows position, not an issue. Okay. If I write x plus y is equals to 1 or x minus y is equals to 3, if I change the position, okay, I can do that. Okay, no issues. So uh, at this point, but there will be issues that we'll be seeing. Okay, so let's try to complete this operation through a generic form. What is the operation we have to do onto maybe onto MATLAB or in any programming language? Okay, so when I choose the pivot element A11, so I'm just going to trying to see this scenario. So this was the pivot element. Now using this, I made this as 0, the next element as 0, and the next element as. So it means the changes start occurring from equation 2 to onwards till equation n. Okay. So let's see what change occur at equation number 2. Okay. So in equation number 2, I have, so let me just write one of the operation and I'll read that. Okay, E2 will be changed with this operation. Okay. So now I am in the algorithm of the Gauss elimination. Okay. I'm saying that this is the operation that you have to perform. So this will be the updated E2. Equation number 2 will be in updated form. So we are going to multiply with some scalar, which is A21 over E11, A11, and we have to multiply this with equation number 1, and then we have to subtract it from equation number 2. Okay. Let's try to see this. So what is this number at equation number 2? A21. Okay. So I'm just going to write equation number 2. It is A21. So I'm talking about the first position minus, so this is fixed. What is the corresponding number to A21? It is A11. So it means it's going to cancel. Okay, if it is non-zero, it is going to cancel, and so A11 should be non-zero because we cannot divide by a non-zero number, a zero number. Okay, so a pivot element should be non-zero. So it means this is 0. It means at equation number 2, the position A21 has been changed to the value 0. Okay, obviously there is a change at this position. So what will be the change? It will be A22 minus A21 A11. This is fixed. So A22 corresponding to A22, we have a number A12. So this will be the number that will going to come at the position A22. But the thing is, we are only interested at this point to make this as 0. Okay, all the cumulative effect will be there. Okay, whatever going to happen at the other indices of the row. Okay, that is there. So the thing is, this operation will make this position as 0. Okay, now let's try to see. There is a number A31. Okay, in the third row, and we have to make that 0 using the same pivot element, using the same equation 1. Okay, so the changes are going to occur at equation number 3, and this will be A3 minus A31 A11 E1. Now you see the position is A31 A31 A11, and the corresponding position to equation 1 is A11. That was A11. So this will be 0. Okay, so this operation will make the first element of the third row as 0. Okay, so if I try to go to the fourth row and ultimately to the nth row, what can I write? En minus a, anyone? an1 a11 e1. Okay, So after these operations, I will have the the matrix will look like this. Okay, so the matrix will going to look like this. Okay, let's try to write all these statement in one statement. Actually, let's try to just write it in a form that it is um, ei. Okay, so ei, and where I is starting from? 2. Okay, I start from 2 and till n, and ei is same as ei minus I1 A11 E1. Okay, so I just write in a very easy form that it is ei is same as this equation. Okay, so only the constant thing if you see in this equation are the indices, which are E1. Then you got the second index of the numerator. Okay, and obviously the in the denominator you see both indices are A11. Okay, so you see a pivot element is being divided in every actually iteration. Okay, in every equation. So that's how you can. Now if the pivot element is A22, I have to make change at A32. So below this point there is A32, then A42, so on to AN2. So it means let's try to write like we just did with this for the second pivot element. So what is our objective? Our objective is same, to make all elements below the pivot elements as 0. Okay, so we start from row number which? The changes are going to occur from row number 3. Okay, so the changes are going to occur from using the row number 2. Okay, using the row number 2, the changes are going to occur from row number 3. Okay, the change is going to occur at row number 3, which is E3 minus A32 A22 E2. Okay, so the element below this is A32. Okay, so that element is A32 minus A32 A22, and the corresponding element in the row 2 is A22. A2. So this bit amounts to 0. You'll see that A32 will now be 0. Okay, so with this operation we can make actually the pivot element below the second pivot as 0. Okay, okay, so we can make it a 0. What about the fourth equation? It is E4 minus A42 A22 E2. You see a pattern? Okay, same as we got in the one, but now there are index 2 is being fixed. Initially index 1 is being fixed because A1 was is the pivot element. If I, what is the last operation we have to do? Onto the nth row. Okay, so it is En minus An2 A22 E2. Okay, and if I ask you to just write this in a generalized way, you can say that okay, this is EI is replaced with EI minus AI2 divided by A22 and E2. Okay, that's how we can, and the I will run from where to where? 3, 4 and till n. Okay, now the next pivot element will be A33, A44 up till which point? ANN or AN minus 1 n minus 1. So I don't need this now because I have this. Okay, this is my first pivot element. Okay, I don't need this now. This is the observation I have. So let me write this over here, which is I from 3 to n minus ai2, e22, e2. So this is the observation with the second pivot element. Okay, so we have to go up till I minus 1, up till the uh, uh, n minus 1 pivot element, because when n minus 1 pivot element will be at the n minus second last row. Okay, we make a row below that as 0, that the element that is lying below the pivot element, then the last will be a and n, and there is no element below a and n, so we have to stop there. It means I have to continue from first, second till n minus 1 pivot element. Okay, and can you write for n minus 1, I will run from which point? I will only run at n, because when we have this value as 1, I runs from 2. When we have this value as 2, I runs from 3. So if I have the n minus 1 pivot element, we have only to run at the last row, okay, which is n, and I can write will be ei minus ann divided by, sorry, okay, am I right? Yeah, I'm right. So the pivot element is n, am I right? It's n minus 1, so it will be n minus 1, n minus 1. Okay, so because it is n minus 1 pivot element, okay, we have to go till now. So I has to run at n. Okay, so using this, I has to run at n. Okay, now let's just write all this into one operation. Okay, so which is ei is ei minus, so I want, so I'm going to generalize what? The pattern 1, 2 till to n minus 1. This the pattern is already been generalized. Okay, we have to now actually collect all these equations and write in a generic form, which is ai j. So let me, rather than 1, let me write j divided by ajj, and this is ej. Okay, so rather than this 1, 2 and n minus 1, I have written j. Okay, so it means j is running from where? Let's try to see. Let's try to see. For that, I need to know I. So let's say j is equals to 1. Let's say j is equals to 1. If j is equals to 1, which is this case, so I will run from 2 to n. If j is equals to 2, will be at this position. So it means it will run from 3 to n. Okay, so if it is j is equals to j, then I will run from which point? J plus 1. I will run from j plus 1 till what point? It always runs from till the n. Okay, the ending point is n. The ending point of I is always n. Okay, so it is from j plus 1 to n. And by the way, what is the maximum value of j? N minus 1. Because when j will be n minus 1, I will only run from j plus 1, which is n. It will only run once, that is, it will only deal with the last row, and this is end and this is end. Okay, so this is the nested loop. It's a nested for loop. Okay, so it is when we try to actually write the Gauss elimination. If you have a matrix, augmented matrix A, if you write this thing into the MATLAB, it will give you a matrix in which you got an upper triangular form. Okay, the next step is obviously the backward substitution. Okay, the backward substitution is over there. So this is the general actually procedure for the Gauss elimination. Okay, for the Gauss elimination, I used to say bisection method since we done so much. We have repeated it so much, the bisection method. So this is the first portion of the Gauss elimination, which is obviously converting into an upper triangle form. Now coming to the issue with the Gauss elimination. Sorry, yeah, with the Gauss elimination. What is the problem with Gauss elimination? The problem is this, which is we call it as pivot element. This needs to be controlled. Okay, so I'm saying my observation is the pivot element needs to be controlled. Okay, we have to control this. Okay, uh, for this, let's take an example. Okay, let's try to take an example and understand through an example. Okay, before I write an example, there is a number, a special number, real number actually. This number is called a machine epsilon. Epsilon. Okay, epsilon. Hopefully you remember this notation. Delta epsilon notation. Okay, epsilon means a smaller number. Okay, we usually try to have this. It is 2.2. So into 10 is power minus 16 is 2 raised power minus 52. Okay, so it is one of the smallest number we have. Okay, that machine can store. Azan हो रही है, break ले ले. Okay, so it is one of the smallest number that machine can store. Okay, so I just try to understand this way that, for example, this is the zero of the MATLAB. Okay, it's a zero of the MATLAB or a zero of any machine. Okay, so um, so it's a very small number. In other words, it's a very small number. Okay, if you take a twice of this number, so for example, if I try to explain in this way that, let's say this is a number 1 in your calculators, okay, or in your machine, in your, for example, MATLAB you're using on the PC, so there's a number 1. Okay, if you add epsilon, okay, over there, it will give you a value 1. Okay, if you subtract it from, let's say, 2, so it will give you a value 2. What we understand in mathematics is this is not 1. This number is greater than 1. This number is greater than 1. Okay? So if I try to write mathematically, I will write 1 plus epsilon is approximately as 1. Okay? But since computers have a limited storage of information that they can store, so a definition of a 0 is different as we understand. They can't go to the infinite decimal places as we have already discussed in the initial lectures. Okay, there are bits by which we store the number into the computer system. Okay, so they are limited. Okay, so you consider it as a number which is the first number after 0. Let's say consider it as the first number after 0. In mathematics we can't find that number, but when we try to use the computers or any machine, since they have a finite arithmetic, so we have to define a number which is first number after 0. Okay, so let's say that this is the number which is first number after 0. Okay, so when you try to write on your calculator, it will give you an answer 1. Okay, but mathematically, if you ask a mathematician, okay, what is this number, it will say it's not 1. It is, if you say this is epsilon, so it is greater than 1, because we can find a number which is obviously less than this number. So for example, 2.2 into 10 to the power minus 32. Okay, 10 to the power minus 52. Okay, 10 to the power minus 100. So if you ask any number, you can find even a number which is smaller than that it means it will be more nearer to 0. Okay, so but since we are using we are using softwares, our solutions can be a rational number, so we have that limitation. Okay, so this number is this is a number for which you will see such a observation on your calculators or onto the PCs you will use. Okay, so for that, let me just write an example, which is epsilon x1 plus 2x2 is equals to 4, and x1 minus x2 is equals to 1. Okay, so let's try to try to find the solution. Simple two equations, not a big issue for us. Okay, uh, first just analyze it. Okay, just do an analysis. Okay, if for example epsilon is so small, we just discussed, then obviously this amount will be very negligibly contributing to the equation. Okay, so we can say that 2x2 will be, okay, let me write over here, 2x2 will be approximately as 4. It means x2 will be approximately 2. Okay, and if I plug this equation into our equation, it says x1 minus 2 will be approximately 1. So in other words, x1 is approximately 3. Okay, so the solution is 3 and 2. I write a transpose because we write it as a column vector. Okay, I'm just writing a row vector, so I just put a transpose. Okay, so this is the solution that we just analyze it, this is the solution we got. Now let's try to uh, apply a Gauss elimination. Let's try to apply the Gauss elimination. Okay, and if I try to use a Gauss elimination, I have to convert it to an augmented matrix, which is epsilon 2, 4, 1, minus 1 and 1. So this is the augmented matrix. Okay, and if we just use the algorithm of the Gauss elimination, it says this is the pivot element. Okay, just use this to make it 0. Okay, So the changes are going to occur at equation number 2. It will be E21 minus A21 A11 equation 1. What is A21 in this equation? A21 is 1, then we have an epsilon, and then we have equation 1. Okay, if we do such an operation, obviously if you choose an element of E2, it is 1 minus 1 over epsilon times epsilon. So epsilon will cancel, 1 minus 1 will be 0. Okay, okay, so there will be epsilon to 4 0, and then we have minus 1 minus 2 over epsilon. Okay, then we have 1 minus 4 over epsilon. Okay, if we do this operation, that's how we'll get it. And now it is in the form where we can perform the backward substitution. So let's perform a backward substitution, which is okay, let me write into the equation. It is epsilon x1 plus 2x2 is equals to 4, and minus 1 minus 2 over epsilon x2 is 1 minus 4 epsilon. Okay, so if I see the equation number 2, it says minus epsilon, or you can just remove the, it's plus 2 is equals to 4 minus epsilon x2. Okay, so epsilon plus 2 x2 into this. I just um, multiply on the both side by epsilon, and I take a negative side common from here. Okay, and travel to. So the calculation. Now we just seen what is epsilon plus 2. It's approximately 2, and this is 4. If you subtract this number from any number, it will be same. If you add to this number, this will be same. So computer will say x2 is equals to 2. I use equality sign here, okay, because so we got x2 as 2. Now if we use x2 as 2 into this equation, because obviously once we have the value of from the last equation, plug into the second last equation, okay, which is ultimately the first one. So if I plug this value over here, epsilon x1 plus 2x2 is equals to 4. Okay, so what is this? If you just try to see this, this is epsilon x1 plus 2 into 2 is equals to 4. Okay, so from here you got epsilon x1 as 0. Okay, or in other words, x1 as 0. Still it's a non-zero number. Okay, so x1 as 0. Now what is the solution we got? What is the value of x1? 0. What is the value of x2? 2. This is a solution which is a near solution, a good solution. We just, because these are simple equation, we just analyze it. Okay, this is the solution. But the solution you just got is not very much near to the solution that we wanted. So actually we have some divergence in it. We have some issue over here. Okay, now before I just point to address the issue, we'll just quickly, so let me just rub this working, and let me write an observation, which is this was the pivot element, and let me write an observation. If pivot element is or let me just write, change the row So I'm just talking to the about the column number 1. Okay, I'm just at this point trying to talk to the column number 1. That is a pivot element A11. Change the row which has maximum absolute number in column 1. Okay, so if A11 is a pivot element, look for the elements below the pivot element. And if there is some number which in absolute terms is greater than the pivot element, swap that row. Swap that row. For example, in this question we have 1. Okay, for example, this is a 3 cross 3 system and there is a -5 here. Okay, -5. So -5 in absolute terms is greater than 1. So we'll have to swap that row with the first row. Okay, so you look for the maximum number in the pivot in the first column and absolute maximum, swap that row with the row number 1. Okay, so in particularly in this example 1 is greater than epsilon. Okay, so if I swap the row, if I impose this observation, I will have the augmented matrix like this. Okay, this is my augmented matrix now if I just impose this condition. Now let's apply the Gauss elimination now. Okay, let's now apply the Gauss elimination. So if I apply the Gauss elimination, it says, okay, you have to do the same operation, but A21 and A11 has been changed. So E2 is going to change with E2 minus A21, A11. So what is A21 now? It is epsilon. And what is A11? It's 1. So it means we just have to subtract epsilon E1 from the equation number 2. Let's do that. 1 minus 1, 1. There are no changes, sorry. Yeah. So there are no changes to the row number 1. And then to the row number 2, this is the operation we have to do. Okay. So epsilon minus epsilon into 1. It's 0. Then we have 2 minus epsilon into minus 1. So it is 2 plus epsilon. Then it is 4 minus epsilon. Now this is the upper triangular matrix converted into the equations. So we have x1 minus x2 is equals to 1 and 2 plus epsilon x2 is equals to 4 minus epsilon. What is x2? It is 2 because 2 plus epsilon is 2, 4 minus epsilon is 4. Okay, so it will be 2. If it is 2, what is x1? If you plug 2 over here, you got as 3. So what is the solution you got? 3, 2. If you compare this solution with the solution we just analyzed and the solution this with the solution we analyzed, you see a difference. Okay, so why this happens? Why this happens? Okay, why this observation lead us to a solution which is better? Okay, which is more realistic. Okay, the thing is, when we multiply by the smaller numbers, it becomes bigger. If you multiply by 10 raised power minus 16, in a numerator it will be 10 raised power 16. Okay, and when you try to see a number 10 raised power 16 into your calculator cannot show it. It will just show that number up to 10 decimal places. So it means, for example, there is a number which is 4 decimal place number. Let's say it is 4217. And your calculator can only show up to 2 decimal places. So what is the number you're going to show? It's going to show 4200 because after second decimal places, it can't show the digits. Okay, and they are significant digits. Okay, now in other way, if you see, for example, this representation, so here you have 2 plus epsilon. No, so now this number is not as big number as compared to this particular number. Okay, so when you divide by a smaller number, for example, you divide by a 0. Let's take this, think this epsilon is a 0. If this is 0, you get what? Infinity. You don't get any answer. Okay, now when you try to get away from 0, you try to put a number which is greater than 0. So let's say put 10 is power minus 100. Okay, so the answer you're going to get is into 10 is power hundreds, and to get the 10 is power 100, you can't actually have any machines which will give you a representation up to 10 is power 100 decimal places, and they all are significant. They are in billions. Okay, so they are in billions. Okay, so when you try to get away from 0, so you see a convergence. So at 0, divide by 0, you have an infinity, and when you try to stay away from 0, you got the smaller numbers. Okay, you got the bigger numbers, that is, you coming towards 1 or minus 1, whatever. Okay, so you're going towards a bigger number in absolute terms. So when you divide by the bigger numbers, you get a smaller number, and rounding the smaller number is easy. You can see that. Okay, to round the bigger numbers, you can't see that. Okay, so this particular observation is to be done at every pivot element. For example, if we are at the first element, we have to see, okay, what is the biggest element below in the column number 1. We'll change it, that row. If we come to the second pivot element, we'll see what is the biggest maximum number, absolute maximum, below the pivot element. Below the pivot element, you don't have to look up the pivot element, below the pivot element. Okay, so if you just use the Gauss elimination and impose this condition has a name. It's called partial pivoting. So it is a pivoting strategy. Okay, it's a pivoting strategy. Your pivot is strategize. We strategize for a pivoting. Okay, so if you do this, it is called a Gauss elimination. The one we were previously doing is called a naive Gauss elimination at times. It's a little a smaller version, or you can say an initial version of a Gauss elimination. Okay, which were we already doing, but this is a better version of a Gauss elimination. That is one with the pivoting strategy. Okay, with the pivoting strategy. So in this particular lecture, we'll just be concluding that we just revisited the Gauss elimination. We actually make an algorithm of the Gauss elimination, and we see what is an issue with the Gauss elimination, okay, and how we can avoid it. Okay, so through the pivoting side. So thank you so much. Thank you so much.